Okay, so it's a great pleasure and honor to talk at this event. So apparently I was the first who congratulated Sinai after the announcement ceremony. And also let me take this opportunity to congratulate him again and also express my gratitude for almost 50 years of guidance, support, and friendship. Okay, so now I go to the content of my talk. So homogeneous dynamics is it's term which is used instead of flows on homogeneous spaces. So it studies dynamics of actions of subgroups of Lie groups on the quotients of this Lie group by a discrete subgroup of this Lie group. So this is G mod gamma, and also there is some subgroup. So one of the basic examples is the example which was mentioned in Sinai's talk. It was automorphism of a torus. And so this is, so one take a torus which can be written as torus Tn, Rn by Zn, and if we have a integral matrix n by n with determinant 1, then there's a linear transformation which is associated with this matrix, and this linear transformation induces automorphism of this torus. So actually this example appeared in the first foundational paper on entropy, and where Sinai introduced the notion of entropy, and actually his main example where he applied this new notion was the automorphism of a two-dimensional torus, and he proved that the entropy of the automorphism of this two-dimensional torus is equal to the logarithm of the absolute value of the eigenvalue of this matrix, where there are two eigenvalues. One is an absolute value greater than or equal to 1, and one is less. So one takes the one which has absolute value greater than 1. And actually, if I remember correctly, so the statement was that for this automorphism of two-dimensional torus, this logarithm of the absolute value of lambda is an invariant of this automorphism. Now so this result was, okay, now I will formulate many extensions and generalizations of this theorem of Sinai. They can be attributed to various people, but somehow the method of the proof goes back to this original paper, or first paper of Sinai, and also some later papers of Sinai, in particular paper about measurable partitions and so on. Okay, so now some of these generalizations. So it's in the for general n, so there are, of course, many eigenvalues with absolute value at least 1. And so instead of just taking logarithm of absolute value lambda, one should take the logarithm of the products of all these eigenvalues with absolute value at least 1. And one, of course, has to count this with multiplicities. Okay, now so there will be some rather technical statements. So one can consider this more general, these translations on G mod gamma. Then there is So assume that gamma is a lattice, and that means that, so it's a discrete subgroup such that the quotient has finite volume, and this, okay, now one take translation by some element of G in this group G, and then then there's a translation which corresponds to this element G, so we just take left translation by element of G. So you take element X in G mod gamma, then X goes to Gx. Then the entropy of this linear, of this translation with respect to the Lebesgue, with respect to this Haar measure on G mod gamma will be equal to the logarithm of the products of absolute values of all eigenvalues with absolute value at least one. Actually, one has to take logarithm of the product of the absolute values of all eigenvalues. And this product can be actually expressed as the absolute value of determinant of what I denote here at G of plus, where at G of plus denotes the restriction of the adjoint at of G. So we take a joint representation of this group G and restrict to this Lie algebra of the group U plus of G, which consists of element X such that when we conjugate this element X by powers G to the N, and when N tends to minus infinity, then it goes to 1. So this actually, this group U plus of G corresponds to unstable foliation of this translation T of G. And then it's possible this entropy will be equal to the, log of the absolute value of the determinant of G of plus. Now, actually, there's a very important fact about the entropy, which is actually not completely obvious, that the entropy of an automorphism is equal to the entropy of its inverse. And so therefore it's possible to rewrite this entropy H of T of G of M as a minus of the logarithm of determinant H of minus, where H of minus is defined analogously to the H of plus. So instead of U plus of G, one considers U minus of G, and then one takes elements X and G such that you will conjugate this X by this powers to G to the N, then it goes to 1 as N tends to plus infinity. And this corresponds to, this group corresponds to stable foliations. Okay, so this is about the entropy of translation T of G when one considers this invariant measure on G mod gamma. But there is also interesting to consider this for another invariant measures. And there is a following statement: if we take for any other invariant measure, then the entropy can only decrease. And you will have equality, then the measure mu should be invariant under both U plus of G and U minus of G. And so, as I said, these orbits of u plus of g and u minus of g are exactly the leaves of this expanding and contracting foliations. And then it's one has, so there's several statements. So it's, you will consider this TG invariant probability measure, then there is one can consider conditional measures on the leaves of these stable and unstable foliations. And actually it was one of the main tools introduced by Sinai. So these conditional measures are defined after the multiplication by a constant. And then there's a generalization of the statement which was on the previous page, when we consider measures which such that conditional measures are supported on orbits of some subgroups of u plus of g. And then there is a rather technical statement that actually just I want to say that it's, so when we have this measure mu is f invariant, then we have an inequality which is analogous to the inequality which was on the previous page. And so then there was a statement that if this conditional measure is supported on fx for almost all x in G mod gamma, then we have this inequality. And the equality holds if and only if mu is f invariant. Okay, now there's a rather technical, it's a quite technical proposition which I don't want to explain in all details, so just the meaning of this. So if we have this, so there's a picture which maybe will be more useful. So suppose we have this point x in G mod gamma and assume that there's a conditional measures which on u plus of g of x should be on this orbit fx, where f belongs to u plus of g. And on u minus of g, it will be on the orbit px. And the statement if the somehow expansion in the direction of fx, instability, will be not less than contraction in the direction of px, and if the measure is invariant under f, then it should be also invariant under p. And actually, and then actually one has that the contraction should be, so the property free, that we should have equality. So so I will return to this proposition later when I talk about this, actually go more closely to the homogeneous dynamics. Okay, so now it's, so Sinai had almost about 70 graduate students, and in the rest of my talk I will mention only 3 of them. One is Marina Ratner, Anatol Katok, and myself. So Ratner and Katok made outstanding contributions to the area of homogeneous dynamics, and modesty forbids to talk about, to comment on my own work. So now, despite the modesty, so I will explain some results which is related to the interaction between homogeneous dynamics and number theory. So it's one of the exciting applications of the area of homogeneous dynamics. Okay, so one is about the quadratic forms, and there is a following theorem, which is that if we have a real irrational indefinite non-degenerate quadratic form in at least 3 variables, then for every positive epsilon, one can solve in integers. So there is non-trivial solution of the inequality that absolute value q of x1, xn is less than epsilon. So it's maybe one comments about this theorem. So it's the most difficult is for the case when n is free, and this is based on the remark that we can, if it's proved for some smaller m, then it's easier to reduce to get for all greater n, and this is because of the remark which is here, that if we have this form q that, and we have m between 2 and n, then Rn contains rational subspace of a dimension m such that restriction has the same property of the original form q. So actually this is a type of instead of b should be q. Okay, so this was conjectured by Oppenheim, and I proved it in mid-80s, so it was published in 1986. And originally the conjecture was stated only for n at least 5, and there was motivation for the conjecture was the classical Mayer's theorem, which is about rational forms, and which says that if we have a rational quadratic form that in at least 5 variables, it's okay, it's not written here, it should be indefinite, then there exists x, and then this form represents non-trivially 0. So it's, okay, we have q is a non-degenerate indefinite rational quadratic form in at least 5 variables, then there exists non-zero vector x such that q of x is 0. Now it's, okay, there is a remark that for n is, the condition that n is at least 3 cannot be replaced by the condition that n is at least 2, and there is an example that one takes x1 square minus lambda x2 square, then it can be written as a product of 2 linear forms, and if there is a square root of lambda satisfies the condition that continued fraction development has bounded partial quotients, then it's easy to see that this infimum of values of this form x1 square minus lambda x2 square at integral points will be strictly positive. An example of such lambda is written, so 1 plus square root of 3 square, which is 4 plus 2 square root of 3. And actually it's maybe the special case, which is probably looks rather elementary, but somehow it's as difficult as the general case, and one takes this quadratic forms x squared plus y squared minus square root of 2z squared, or x squared plus y squared minus square root of z squared, then for every positive epsilon, so there is non-trivial solutions and integers for this inequality. So we take absolute values of these forms, and it will be at least epsilon. So it's always trivial solution. So let me repeat, so this is as difficult as the general case. Okay, so now the proof of this statement about quadratic form actually uses topological dynamics, and this is essentially due to a suggestion by Raghunathan. And so then there is a statement which in fact is equivalent to the statement about quadratic forms. So one take group G, which is the group of 3 by 3 real matrices, and take subgroup of this group G, which consists of elements which preserve the form 2x1, x3 minus x2 square. And now one also the notation is for SLN R by SLN Z, so this quotient can be identified with the space of unimodular lattices in Rn. And the theorem is, okay, there's a dynamical statement which is, if we take a point Z in this quotient space and take the orbit of Z under H, then this orbit is, and if this orbit is relatively compact in this omega free, then actually this orbit is closed. And there's equivalent statement that the quotient of H by the intersection of H with the stabilizer of this point is compact. So this is actually quite opposite to the hyperbolic dynamics when one has the behavior of bounded orbits can be extremely complicated. So in some sense it's maybe opposite to chaos, okay, but only in some sense. Now so actually after this theorem about quadratic form was proved, so because I looked and other people looked at the old paper of Cassos and Swinnerton-Dyer from 1955, and in some implicit form the equivalence was there, but really when I met Swinnerton-Dyer and asked, did you know that you had this equivalence, he said, no. But actually one looks at the paper that one can find all necessary ingredients for proving this equivalence. Now so Raghunathan already discovered this equivalence, but more importantly that he realized that the Oppenheim conjecture would follow from a conjecture about closures of orbits of unipotent subgroups. So unipotent subgroups, so there's unipotent matrices which are matrices with eigenvalues 1, all eigenvalues equal to 1, and so unipotent subgroup, of course, a subgroup which consists of unipotent matrices. So then this conjecture by Raghunathan is the following. So you will have a connected Lie group, and gamma is a lattice in G, and U is a odd unipotent subgroup of G. So odd unipotent means that if apply a joint representation, that subgroup becomes really unipotent, that all eigenvalues will be equal to 1. And Raghunathan's conjecture is that if we take a point x and G mod gamma, then if we take the closure of the orbit and of x under u, then it will be actually orbit of the some another closed subgroup. So actually there's some additional statement about this. So I will come back to this conjecture later, which is now a theorem. But let me mention that, so actually this statement about bounded orbits and also some other generalizations which were proved shortly after the Oppenheim conjecture was proved by Daniel and myself. So I just prove some of this special case of Raghunathan's conjecture. Now there was a slightly more general statement about quadratic forms that shows that you will have the same form Q with the same conditions, that the set of values of this form Q in integral points will be dense in R. And this is written in slightly different form. Okay, so now we'll go to some quantitative statements about the number of solutions. So we have that we can solve this inequality Q of x1, xn between a and b in integers. But what can we say about the number of solutions? Of course, the number of these solutions should be infinite, but what can we say about number of solutions in integral solutions in certain domains? Okay, now there's first my description of this domain. So we take some star-like domain, and then we take the number of solutions in the dilations of these domains. So there's the integral solutions, and then they take the volume of the real solutions. So we take when x in this dilation and Q of x between a and b, and then there's the volume. And now there's now there's this asymptotic formula for the volume, which is quite easy to prove, that there's a T to n minus 2 multiplied by the difference between b and a, and also there's some constant which depends only on omega in this form Q. Okay, now there's this picture, so it's one takes, for example, if omega is a ball, then when multiplied by t, then we have this ball of radius t, and then we count the number of integral points in this domain, which is here, so it becomes very thin when we go to infinity. And so we're interested in some estimates for the number of solutions. And now there is a statement which was proved by Daniel and myself, so that there's some lower bound if we have this quadratic form in at least 3 variables, and there's we take OPQ, there's so signature PQ, and P is at least 2, and Q is at least 1, then for any rational form, we have this lower bound for this lim inf, so it's at least 1. Okay, so there's extensions of this, okay, there's some more precise theorem about asymptotics and upper bounds, but I don't have time to talk about that. Okay, so now there is a conjecture of Dani, which was conjecture of Dani, which was again now a theorem. So if we have an invariant measure which is finite and invariant under U and ergodic, then there exists then this measure will be a Haar measure on the orbit of some bigger subgroups, and these measures can be called algebraic. Okay, so now I mentioned this Raghunathan's conjecture and Dani's conjecture, and so all these conjectures were proved in full generality in a landmark series of 4 papers by Marina Ratner. And so now I will state the orbit closure theorem, which is due to Ratner, and which is actually is more general than the proof of the Raghunathan's conjecture. And so one considers not only unipotent subgroups, but subgroups were generated by one parameter unipotent subgroups. And then there's a statement that the closure of any orbit will be, again, orbit of some subgroup, and this orbit should have invariant probability measure. Now actually the main theorem in Ratner's book, actually this maybe not just this orbit closure theorem, and there's a theorem about measures, but which will be mentioned a little bit later. But this is equidistribution theorem, which is so there is a classical Birkhoff ergodic theorem that if you have an invariant measure, then ergodic, then if you take for almost all points, the average should be asymptotic average should be equal to the integral. But this theorem doesn't say anything about individual orbits, and in this equidistribution theorem is actually the statement that for every point x, there exists some measure such that this average, if we take of some bounded continuous function, and average of a trajectory from 0 to capital T and divide by t, then the limit exists and is equal to the integral of f with respect to some probability measure. And actually this probability measure will be a measure on some closed orbit. Okay, so the hardest part in the proofs of the equidistribution theorem is this, okay, the measure classification theorem, which is actually, it's again, more general, it proves the conjecture of Dani in some more general form. And so again, one replaces unipotent subgroup by subgroup generated by one parameter unipotent subgroups. Okay, so now there is, okay, so this equidistribution theorem, so there's as I said, hardest part, it's the measure classification theorem, but also it involves some other ingredients. So there is in particular, the quantitative recurrence to complex sets, so I don't have time to explain this in more detail. Okay, so now maybe I just want to So I stated this proposition, which was in the first part of the lecture, and so I want to explain the relevance of this to this measure classification theory. So the Ratner's proof was quite long, so it was more than 150 pages, and a different and much shorter proof was given by Tamanov and myself. And one of the main ingredients in our proof was based on the proposition which was in the first part of this lecture. So maybe I go quickly to this proposition. Okay, so this is quite long and technical proposition, but somehow it involves this entropy and the estimates for the entropy. Okay, so now it's in the last part of my talk will be related to the actions of multidimensional abelian groups, and also to another conjecture which is due to Littlewood from 1930. So this is again looks very elementary. So for every real number x, we consider the distance between x and the closest integer. So it's not exactly there's a fractional part. If the fractional part is less than 1/2, then it will be this bracket x. But if it's greater than 1/2, one has to take 1 minus fractional part. And the statement is that, the conjecture is that if we take any two real numbers alpha and beta, then the lower limit, if we take n multiplied by bracket n alpha, bracket n beta, will be equal to 0. So this is a very elementary the conjecture with which is the statements are very elementary, but it still has not been proved. And actually, so I mentioned this conjecture. I mentioned the paper by Castles and Swinnerton-Dyer, which was from 1955, and they discussed the Oppenheim conjecture and this conjecture of Littlewood, and also, again, there was essentially there was this conjecture too, if we take, which can be considered kind of analog of the Oppenheim conjecture. So instead of a quadratic form, we consider product of linearly independent linear forms. And for example, n is free, so the product of 3 linear forms. And the statements are what's analogous to the Oppenheim conjecture, if this form is not a multiple form of rational coefficients, then there is a non-trivial solution for the inequality when the absolute value L of x1, xn will be less than epsilon. So again, so in this conjecture, n is at least 3 cannot be replaced by n is at least 2, and actually the example is exactly the same as was for quadratic forms. So you remember there's a quadratic form which was the product of 2 linear forms. And actually it's rather strange that, or quite ironic that in this paper by Carsten Swinnerton Dyer, so they probably considered Oppenheim conjecture more difficult, and probably the reason that the structure of the orthogonal group is more complicated than the structure of the diagonal group. So now there is a kind of dynamical reformulation of this conjecture. We take, again, SLNR by SLNZ, and instead of the orthogonal group, take the group of all positive diagonal matrices, and as again as at least 3, and the statement if the orbit is relatively compact in G mod gamma, then AZ is closed. Okay, so now there is so as I said, the Oppenheim conjecture has not yet been proved, and so probably the best, the strongest result is due to Manfred Einstein, Anatol Katok, and Elon Lindenstrauss, and they proved in 2003 that the set of exceptions of Littlewood conjecture has Hausdorff dimension 0. So it's quite easy to show that the set of exceptions to the Littlewood conjecture has Lebesgue measure 0, but essentially it says that for all, but it's much stronger. So if it take more or less any reasonable measure, then with respect to this reasonable measure, the set of exceptions to the Littlewood conjecture should have measure 0. And again, so actually the crucial argument, actually the entire proof based on the study of A-invariant ergodic measures with positive entropy. So there's this, actually it's, so the paper by Einstein, Katok, Lindenstrauss itself is pretty long, but it's also is based on quite many other previous results. For example, there's papers by Katok and Spatzir, there's papers by Einstein and Katok, and then by separate paper by Elon Lindenstrauss. And so there is, no, actually there's some remarks. So there's two cases which they called high entropy case and low entropy case, and so the high entropy case studies measures for which many one-parameter subgroups of this diagonal group A have positive entropy, and so this case mostly was handled by methods which due to Einstein and Katok, and then the measures with low entropy but positive entropy when we have this positivity of measures only for some subgroups. And so as they notice in their paper, so that somehow these two methods are completely complementary. So it's, but again, so the crucial method is using entropy and actually in a very elaborate way. So using conditional measures and so on. So this is, so just at the end of my talk, so I want to emphasize that, so probably this, as I said, somehow this results from homogeneous dynamics, somehow maybe for about actions of big subgroups, and in a sense it's opposite to chaos, but as it turns out, so there was quite many arguments involves this notion of entropy, which is very related to chaos, and so it's again, it's maybe not surprising, but it's just so somehow it shows the power of this notion of entropy, the conditional measures, then invariant measurable partitions, and so on. Okay, so this I finished.